there's different kinds of behavior that you might see in these math spring systems. And because of the assumptions that we're making about the values for these parameters MC and K, you only have essentially 4 types of behavior. And you should be able to recognize them and understand their names. So the names that you'll see: undamped, underdamped, critically damped, overdamped. And essentially you should be able to sort of say, okay, what's going on in these situations? And if you just think about what's going on, so there's 2 things involved. There's a spring. Springs want to be springy. They want to do this, keep going up and down. Dampers are like, no, don't do that. They try to stop that motion. They're trying to slow it down. So the undamped says there's no damping at all. It's just pure spring. And so your solutions look like combinations of cosine and sine, which basically, when you put it together, looks like a sine curve or a cosine curve, essentially the same thing. So undamped means no damping, C equals 0. All right, no big surprise there. Underdamped, well, you should think of the underdamped as saying there's a little bit of damping, but not much, not much. So what's that? Well, the spring still acts like a spring, but the damper is starting to slow it down over time. So in particular, there's sort of this exponential decay over time, so that the oscillations up and down get smaller and smaller with time. So the roots look like negative A plus minus BI. So that there's just this exponential decay happening with your motion. Now we can just say, you can memorize, oh, that means that C squared is between 0 and 4mk. If you're wondering where is this coming from, this is coming from, use the quadratic formula. And if you use the quadratic formula on this equation, this is what pops out. How can you get in that situation? I'll jump over critically damped and say overdamping is lots of damping. That says, like, I put an industrial strength damper on it. It's so powerful that it overwhelms the spring. And so that you don't even get to do like a full oscillation. And so what does it look like? Well, maybe it crosses once, but never twice. It just goes back quickly, exponentially quickly, towards 0. And that's when you have distinct negative roots. Critically damped is when you're in that sweet spot. So what do we mean? You're right on the edge. You know, if you were just slightly less damped, you'd have this infinite oscillations happening. And so it's just right on the edge. So that's what critical damping is. And in terms of the roots, it means repeated negative roots. Okay, so those are the types of behavior. That's where we finished with last time. Any questions on that? Okay. So we have a few notes. So, start with the undamped. So the undamped says, okay, suppose I have something in the form C cosine bt plus D sine bt, and the claim is we can rewrite this in the form A cosine bt minus theta. Now, everything we're about to do is nothing with differential equations. Everything we're about to talk about in the next 10 or so minutes is trigonometry. So, time to channel your inner trig. All right. So how do we go from here to there? Well, we begin by doing the following. We're going to factor out this term, square root of C squared plus D squared. And I'm just going to pull it out of this expression. Now you might say, but Steve, it's not even there. Why pull it out? You'll see why in a moment. So what you have is C over the square root of C squared plus D squared times cosine bt plus D over the square root C squared plus D squared times the sine of BT. All right. Now our great, let's think of this first piece, c over the square root of c squared plus d squared. We'll call that x. D over the square root of c squared plus d squared, we'll call that y. What can we say about x squared plus y squared? So c squared over c squared plus d squared, that would be our x squared. And then we have d squared over c squared plus d squared, that's our y squared. And if we add those together, we get c squared plus d squared over c squared plus d squared, which is 1. Yes. All right. Well, if I see something like the form x squared plus y squared equals 1, what do I think about? Someone said circle. What circle? Unit circle, yeah. People are like, oh, hey, there's like keywords over here. Yes. So that says our great, okay. So we can draw our favorite circle, the best circle. We say, all right, here's our point x, y. It's on the unit circle. And now we dig a little bit deeper into our trig background. How do we think about points on the unit circle? Sorry, what? Cosine sine. Okay. So, in particular, someone said cosine sine, which means that there's some angle, let's call it theta, where this point is cosine theta sine theta. Because I can think about every point as being related to cosine and sine of some angle. Just, how far did I have to go? All right. So what we really have up here is that this part is a cosine, and this part is a sine. Now, let's recall a fact. So this is a trig fact. And, whoops, if I can spell fact. If I look at cosine alpha minus beta, does everybody know this formula? Cosine alpha minus beta? I'll start it. It's cosine alpha, cosine beta, plus sine alpha, sine beta. All right, now if you stare at this, and then you stare at what we have, you might be like, what? We have a cosine, cosine, sine, sine. Cosine, cosine, sine, sine. So that this piece here is really a cosine of a difference. So in particular, this becomes the square root of c squared plus d squared. And now the question is, well, which one do I subtract? It doesn't really matter. So we'll write it as cosine bt minus theta. And so our last thing is just to say, hey, that thing out front, we'll call this A. So that's how we go from that expression to that expression. It's some trig. Okay, so now we have sort of a sense, okay, what is A? Well, what we have is essentially a cosine because it's a cosine. So that A is saying how far up do we go? So it's an amplitude. So that's why we have the amplitude is the square root of c squared plus d squared. Now the question is, how do you find this angle theta? Okay, and if you've been doing the homework, this is probably the most annoying part of the homework. So let's talk about that so that we can at least understand how we're supposed to do it, and then curse Math Lab, my Math Lab, for how it makes us do it. Okay, so now we come to our picture and say, all right, the picture says that theta corresponds to this xy point, and we know what x and y are. So we look for ways, how can we go about finding theta? And so probably the easiest thing is to say, let's look at tangent. So what is tangent? How do you compute tangent? Sine over cosine, which in terms of the unit circle becomes y over x, which in terms of our values becomes d over c. All right, so now we have our tangent of theta, and that's a completely correct statement. How do we get theta? Oh, arctangent. What a great function. Okay. So, is that correct? Plus or minus arctan? Okay. So, so here's where things get messy. This first statement, tangent theta equals d over c, 100% correct. This statement is about 50% correct. So you need a fudge factor. Now you might say, where does that fudge factor come in? Now someone was saying, may not be able to have heard them. I was hearing what they were saying. I was saying, well, look at the arctangent. Where does arctangent go between? Do you remember? Plus minus pi over 2, which means that arctangent is in here. So if it so happens that if you think about your coordinate, so you're thinking about, okay, so what do we have? So C and D are giving us our x and y. So here, this would be C is positive and D is positive. We'd be in the first quadrant. Life is good. Arctangent works great. We're happy. C is positive. D is negative. We're in the fourth quadrant. We're still okay. Maybe we want to shift by 2 pi. But yeah, no problem. But things get dicey when we're over here. So here's a case where C is negative and D is negative. And then here is the place where we didn't plan well, and so we don't have enough room. So how do we fix it? Well, the answer is, if I try to plug it in here, what ends up happening is it gives me a point down there. So if I were to plug this value for C and D, it would say, oh, you meant this C and D down here. That's what would come out. So how do I correct? Add what? Yeah, it's halfway around. So your fudge factor is pi. But only if you need it. So then that's the case of you have to see where are you at in terms of the circle. So that's what's showing up. All right, so that's how you go about finding your theta. Okay, so there we go. So there's the fun part. Then most of the rest of this is just various terms that you might see. There's the time lag. And the idea of the time lag says what? Well, you really should think of this as a cosine, and then factor out of b, t minus theta over b. And so in terms of time, if there was no term there, that would be just like a normal cosine. This just says how much are you shifting your cosine. So that's what the time lag measures. Your period, a normal period for a cosine function is 2 pi. The factor of b is really stretching or squishing your input. And so to see how it affects the period, you take 2 pi over b. And then your frequency, it's the reciprocal of your period. How many times, how many periods do you cover in one time interval? All right. So that's some notes on undamped. Any questions? All right. Cool. Good. It's nice to remember trig. Now, I found for me personally, the best way for me to remember trig was teaching it for 2 years. Now, for you, you might want to try something else, or just remember we're testing you on differential equations and not to worry too much about trig. Because we are testing you on differential equations and not trig. Under damped notes, there are some similar ideas, but there's sort of less going on. Now, if you remember underdamped, that's the case where we kind of look like cosine and sine, but what's happening is that our oscillations are going down over time. So we have something going on like that. So this is not a periodic function, because a periodic function would say, if I look here, if I shift over, I look the same. Well, I don't. I look sort of taller than when I shift over there. So it's not periodic. So we can't talk about what's the period, but it's kind of periodic, because there's this sort of periodic nature to it. So in particular, we can do something similar, which we can say, well, if we just pulled out this e to the minus at, it's the same setup as we just talked about. So there's this extra e to the minus at in front. So that the amplitude looks like a constant times e to the minus at. So that is this sort of upper and lower envelope here. So that's what's being captured by this a e to the minus at. Is that, that envelope going in. The pseudo period says, hey, look at the period for that cosine of bt minus theta. And then there's something called the pseudo frequency, and I don't know why, but according to the book, that's b. I'll just accept that as is. And that's all I want to say about the underdamped. Okay. That's good. Okay. Which finishes what we were planning to cover. And then I took a look at the list of topics from exam 1. And something jumped out to me. Well, not because it was highlighted, but I highlighted this one phrase. Reduction of order. Do you remember when we talked about that in class? No. Yeah, exactly, because we didn't talk about it in class. And then I went to the other instructors' notes because they had their notes available to me. And they don't talk about it in their class either. But apparently it's something we're supposed to talk about. Now, the good news is we've kind of did it. We just didn't give it a name. And you have done it on the homework. But since it's on the list of things that you're supposed to be able to do, we should talk about it. And it's great because it's going to foreshadow things to come after the exam. So, reduction of order. Now, it's a lot simpler than this looks. What is the idea, the philosophy about reduction of order? Well, go back to when we were talking about finding roots of polynomials. And we said, well, suppose you're faced with a high degree polynomial and you're looking for a root. What did we say you should try? Do you remember? Guess. Okay, so you found a guess and you say, aha, I succeeded. And then what happened next after you did a guess? Long division. We said because we were able to find a solution, we were able to go through a process to simplify to help us find the rest. Now, the reduction of order captures that philosophy. Says, hey, suppose we have a solution. Now, it came from somewhere. Let's not worry about where. Details, details, details. But suppose you have one. Let's use that knowledge that we have a solution to help simplify the process of finding our next solution. So that's what reduction of order is. Saying, let's sort of leverage one solution to help find another. So, we have a differential equation. We have a solution. And we say, okay, we're going to find our next solution. And the way we're going to find it is we're going to say, let's sort of modify our known solution by some unknown function u times y1. So if we knew what u was, we multiply it by y1, and we say, there's our new solution. Now, we don't know what u is. The goal now, find u. Find u. I feel like I'm in a philosophy class. You need to find u. Be the best you can be. All right. Well, okay. No big surprises. Take y prime, product rule. Y double prime, lots of product rule. And now we're going to substitute y prime, y double prime into our original differential equation. So here's y double prime. P of x, y prime, see there's y prime, q of x times y. Okay. So we substitute in. We rearrange. And here, when we rearrange, the way we're going to do it is we look at our factors of derivatives of u. So we say, okay, say u double prime, u prime, u. So there's only a single u double prime, and that has a coefficient y1. All right. How about u primes? Well, there's the u prime. There's another u prime. So 2y1, p of x times y1. Okay. How about u? Well, there's a y1 double prime. There's a p of x y1 prime. And there's a q of x y1. Now, you'll see something that says underneath that, everything attached in front of the u, it says that equals 0. Why does that equal 0? Sorry, what?
Original equation.
But why does that equal 0 in the original equation? What's the key? It's a solution. It's a solution. See, we know that this, when we plug y1 into here, we get 0. That's what happens. So, see, that's why we get a reduction. We get a 0 here. Now, you might say, but wait, is it really a reduction? Because that looks like a second order derivative. But what we can do is we can do something really simple. We can say, look, this u prime, let's give it a name v. What does u double prime become? V prime. And so we essentially now have, instead of a second order differential equation to solve, we have a first order, which means that we've reduced the order. And that's what reduction of order means. Reduce the order to help us solve. So, an example. Verify that y equals e to the x is a solution to the differential equation x minus 1 y double prime minus x y prime plus y equals 0. And use reduction of order to find a second solution. Okay. All right. So, we've got half of class left. We probably can finish this problem. So, let's begin. No, come on. It won't take half of class, I hope. So let's start with the verify. And you should be comfortable with doing verifying problems, because that's an important tool. So we're going to take x minus 1 times the second derivative of e to the x minus x times the first derivative of e to the x. And we're going to add e to the x. So in other words, I'm putting e to the x into these spots wherever we see y. But now we come to the question, what's the second derivative of e to the x? E to the x. What's the first derivative of e to the x? E to the x. What is e to the x? E to the x. E to the x, our favorite function. Multiply out x e to the x minus e to the x minus x e to the x plus e to the x. And what do you see? Yeah. Pew, pew. The e to the x is canceled. Pew, pew. The x e to the x is canceled. And we're left with 0, which is what we want. It has been verified. So, we have found one solution. Well, we haven't found it. They told it to us. But okay, we were told one solution. And we know for sure it works. Now to find the second one. Okay, so we can either repeat this process or sort of like jump ahead. Do you have a preference? You okay with me jumping ahead? Jump ahead? Okay, all right. As long as you can remember, if you're on a test, you might want to repeat the process if you can't remember. But all right, jump ahead. We'll do that. Okay, so let's see, where are we at? So we're going to say that y looks like some function u times the function we know about. We know about the function e to the x. And we're trying to figure out what the function u is. So according to this, we're going to take our y1, which for us is, it's a solution we know about, which is e to the x times u double prime plus 2 times the derivative of our function we know about, which is e to the x, plus p of x. Okay, what is p of x in our case? P of x is what's in front of the y prime. Which is, we want to say negative x, but is it? No, because what's here? 1. So is that p of x? No. What is p of x going to be? So this is why sometimes it's easier to just sort of plug in and run through the whole process again. Okay, so if we are going to just copy the formula, we have to make sure we have in the right form. So we have y double prime minus x over x minus 1 y prime plus 1 over x minus 1 y equals 0. Okay, so p of x would be minus x over x minus 1. And then times y1, which is e to the x, and times u prime equals 0. Okay, so there we go. So now we have to solve for u. And once we solve for u, we'll be most of the way there. All right, where to next? Where do we go? I'm sorry, what?
Substitute u1 with v. To reduce the...
Oh, so you want to, v and v prime is how? Okay, we can do that. So this will be v, this will be v prime. Notice everything has an e to the x. What can we do? Yeah, we can divide out. Okay. So what do we have? We have v prime from here plus, let's do some stuff called adding, because we have 2 plus this thing. We'll do it in slow motion here. So it'll be 2 times x minus 1 minus x over x minus 1, and times v equals 0. Okay, so what technique should we use to solve this? It's a first order differential equation. We have a couple techniques. What technique should we use? Okay, someone has suggested it's linear. It's a linear first order differential equation. We can use that. Is there any other method we could use here? Now keep in mind, sometimes some problems have multiple ways you can do it. Okay, somebody suggested it's separable. Is it? It is. It is separable. So, would you rather do linear first order type thing, integrating factor, or would you rather do separation of variables? Okay, I'm not saying that there's a right or wrong answer. I am saying that some methods are shorter or faster. It's not always obvious before you begin which way is a short or fast way. All right, we need a little bit more space, so we'll add some space over here. So, what do we mean by it's separable? Well, the v prime, we can write that as dv dx. And when we move this across, we'll say that's equal to minus x minus 2 over x minus 1 v. Okay, or 1 over v dv is minus x minus 2 over x minus 1 dx. So that's separable. We can separate the two variables. So we have to integrate both sides. So, all right, I'll make a deal. I'll integrate one side if you integrate the other. I'll even let you pick. Which side do you want to integrate? The left? Okay, all right. You can take the left. I don't mind. What's the integral of 1 over v dv? Natural log v. Okay. All right, good. Natural log v. All right, so you gave me this side. Well, looking at that, I can't help but notice that x minus 2 looks a lot like x minus 1. In fact, this is a true story. Turns out that x minus 2 is x minus 1 minus 1. No, it's true, I promise. Okay? Now you might say, how does that help us? Well, what's x minus 1 over x minus 1? 1. Yeah, so this is really, don't forget the minus sign. So this is really minus 1. Minus minus makes plus 1 over x minus 1 dx. See, I'm secretly having you help me solve it. So that becomes minus x plus log of x minus 1. And then, of course, because we don't want to lose any points, plus c, yeah, because we want all the points, Okay, now I need to solve for v. How do I get v out of the log? Yeah. So we're going to take both sides, e power that. So we get that v is equal to what? Okay, someone said there's a constant, because e to a constant is a constant. What else will there be? Okay, e to the negative x. I agree. Oh, and then there's a suspicious gap that we can put x minus 1 in. So some constant times x minus 1 times e to the minus x. And are we done? No, because what is v actually? It's u prime. And what are we after? We're after u. So what do we need to do? Integrate. Okay, great. Well, the integral of u prime, that's pretty straightforward. What's that going to be? U. Okay, so how do you integrate? The constant is the constant. All right, it is what it is. So how do you integrate x minus 1 times e to the minus x? What technique do you need? Integration by parts. So if you have two functions multiplying together, it's integration by parts. And the idea of integration by parts is to say, part of this I can integrate really well, and the other part, not so much, but I can differentiate. So there's sort of a trade-off. I integrate one part, I differentiate one part. Now, are we going to integrate or differentiate the x minus 1? Differentiate it, because that makes it simpler. And on the other hand, if we integrate or differentiate e to the minus x, what are we going to end up with? We're going to end up with negative e to the negative x, whether we integrate or differentiate. So it doesn't matter. So yeah, so definitely we'll want to do our quick differentiation there. So integration by parts. Ooh, we should probably remember that. Okay, so if I'm integrating, we can write this as f g prime. That's f times g minus the integral f prime g. So that's what I mean when I say, you integrate one part, g prime went to g, you differentiate the other part, f goes to f prime. So in this notation, some people also use the u db notation. The reason I'm not doing that is we already have u's and v's showing up in this problem. And that's kind of dangerous when you have like the same symbol showing up in multiple different ways. All right, so we said this part we want to differentiate, this part we want to integrate. So, all right, f equals x minus 1, g prime equals e to the minus x, f prime, derivative of x minus 1, 1, g, negative e to negative x. So we are up to f times g, x minus 1 times minus e to the minus x, minus, and then we have the integral of f prime times g, Okay, so that's 1 times minus e to the minus x. All right. So minus the integral of minus e to the minus x will give us negative e to the negative x. Plus, well, we've already used c, d, moving our way through the alphabet, yes. Don't worry, we're really going to start moving our way through the alphabet in the not too distant future where we have lots of symbols. Okay, so we now have, don't forget there's a c in front, that u is a constant times this minus. Oh, let's actually clean this up a little bit here. So this is minus x, e to the minus x. Minus minus makes a plus e to the minus x, minus e to the minus x, plus d. What do you notice? Yeah, the e to the negative x is canceled. Ha ha ha, ha ha ha. So this is some constant, x e to the minus x plus some other constant, which, using our sophisticated tools, we can rewrite in a seemingly cheating way, some constant x e to the minus x plus some other constant. Is that a valid what we did? And why? Where did the minus go? Got sponged up into that constant. Why did this constant times that constant just become a constant? Yeah, because you absorb constants. Now, is that our new solution? No. Why? Because y is u e to the x. Okay, so, but we're there. We're right on the doorstep. So our new solution that we worked so hard to find, we take some constant x e to the minus x plus d, that's our u function, times by e to the x. Well, e to the x times e to the minus x becomes 1. So we have some constant times x plus some other constant times e to the x. Now this is our original solution, y1, which will show up in the process. We say, well, look, we already know about that. Well, that's fine. That means that this will be our new solution, which says that our new solution that we worked so hard to find, that we took like 2 pages to find, our new solution is x. So one solution was e to the x, and the other one was x. And at this point, you're probably thinking, we probably should have just guessed x. That was faster than this. We can verify it's a solution, right? Second derivative of x, 0. First derivative of x, 1 times negative x will give us negative x plus x equals 0. So it works. The process works. Wow, fantastic. All right, so now you've seen reduction of order, which means that we truly have checked everything off our list of things we're supposed to talk about, which means in the last 10 or so minutes, a very quick, what have we learned? Okay, so things that we've learned. Oh, there's a question.
What happens if you have higher than second power derivatives? Like a third, how do you do the reduction?
So the question is if you have a higher order than just second. The answer is you do the same process. You let y equals u times your first solution, and you just run it through.
Do you have to get 2 other solutions in addition to the one you're given, since it's 3?
Yes. So what will happen is you'll go from a third order differential equation to a second order differential equation. So it's not the funnest thing to do, but it's not the funnest thing you do. Yeah. Okay. So things that you should do, or should be able to do. Know how to verify a solution. Just means you throw that function into both sides. Do you still get equality? If the answer is yes, you verified it. If not, check your work. Know how to do Calc 1 and Calc 2. So in other words, things with velocity and acceleration. X prime equals a f of t. X double prime equals a function of t. That's one of the first things we talked about. Know a couple of the important models. So population growth and radioactive decay. Those show up in lots of problems. So know what they are, know how they behave. This one shows up so frequently you might have it memorized. So it just says the rate of change of your population or the rate of change of material is proportional to how much there currently is. so that the total population is the initial population e to the kt. It's actually pretty simple to just rederive it on the fly if you need it. Newton's law of cooling is very similar. Really the only difference between the population growth versus Newton's law of cooling is just saying adjust where your zero is at. So this says things either head away from zero or head towards zero. This says things head away or from this value A, the ambient temperature. This part down here is more towards your mixing models. So know how to set up and solve problems that involve mixing. So that's like you have a tank, you have fluid coming in, you have fluid going out. And there's something mixed in with the fluid. And you want to say, well, how is that thing that's mixed in changing? And the answer is, you say, well, look at the ways that things are coming in. How is S going up? Okay, look at how S is going down. And then S prime is things that make S go up, subtract things that make S go down, and you've got your differential equation. Off to the races. What are the races? Well, that's solving first order differential equations. There's 3 categories of ways to solve first order differential equations, and then there's sort of 2 ways to sort of manipulate. So the 3 categories are separable, which says you can write your differential equation. Y prime as some function of x times some function of y. And I should say, don't get cut up by saying, oh, I have to be in x and y or I have to be in x and t. Symbols are symbols. So be adjustable to using whatever symbols problems have. So separable is pretty simple. Separate, integrate, uncomplicate. We like separable. It's a very straightforward process. Next up, linear first order. So that's anything that can be written as y prime plus p of xy equals q of x. Now you might have to manipulate things. You'll see this point down here, which says rewrite, move things around. So you may have to move things around to get to where you're at, but that's fine. Now, if you do have linear, make sure that what's in front of your y prime is the right thing. What should be in front of y prime? 1. If it's not, make it a 1. You say, okay, step 1, find your integrating factor. And you grab what's in front of the y, you integrate that, e to that power. That's your integrating factor. And if you multiply both sides by that integrating factor, then by magic, also known as math, the left-hand side is a derivative of something. And one of our philosophies says, hey, it's easy to integrate derivatives. So the left-hand side becomes easy to integrate, and the right-hand side, well, good luck. Well, it may or may not be easy, but it'll be easy on an exam. So you integrate both sides and solve. Okay, so that's linear. Now exact comes from the scenario where your differential equation came from this setup. F of xy equals a constant. And what you're trying to do when you have an exact differential equation is say, find that function f of xy. Now, how is it starting? Well, it looks like some function involving x and y times y prime plus some other function involving x and y equals 0. And oftentimes, if you see something in front of y prime that just looks completely hopeless and like, this is ridiculous, exact is a good thing to try at the beginning. And what's going on here, the idea is that this m, this is the derivative of the function with respect to y, and that the n is the derivative of the function with respect to x. Keep in mind that they might do a couple of different things. They might write dy here, dx there. They might put a y prime there, so you have to switch, just keep in mind. So make sure you know which part is supposed to be the derivative with respect to y, which part is supposed to be the derivative with respect to x. Once you have that, you say, okay, if it's exact, I have my derivatives, I integrate. So you integrate the part that's supposed to be the derivative with respect to y with respect to y. You integrate the part that's supposed to be derivative with respect to x with respect to x. You say, okay, there's my functions in the various pieces. And now I merge the answers. And we talked about how to merge. So you can go back and look at your notes. So the other thing, we already said, okay, you might have to rewrite, move things around. The other thing that you might have to do is substitution. Substitution, the goal in substitution is to simplify your differential equation. So things you should look for things on the inside of functions. So you might have some linear term. Okay, then that's your substitution to make. You might have homogeneous differential equations. That's y prime equals to f of y over x, z equals y over x. You might have Bernoulli. That's y prime plus p of xy equals q of xy to the n. It almost looks like linear, except you have this extra piece here. And so if you have that extra piece, z equals y to the power of 1 minus n. And then you're off to the races. All right, so that's the first order. Some other things. Know the logistic model. Now, you'll notice there's this little comment here. You don't have to memorize. Now, what does that mean? It means you don't have to memorize. But you do have to know how to use it. So you still might see a problem involving the logistic model, and you have to say, okay, can I use this formula in the right way? So in other words, identify things like m, p0, your k, and put it all together. Know your autonomous differential equations. That means y prime equals f of y. And here, you don't solve. So that's actually great because it's a differential equation problem where you don't have to solve it. What do? You say, okay, where are the interesting points? And the interesting points are constant solutions. That's where f of y equals 0. You say, okay, now all the other points, what do? Well, they have different behavior. So you plot where f of y equals 0, and then you look at the sign. Because the sign tells you the behavior. Where something's positive, you move up. Something's negative, you move down. So you might have things doing something like that. And now you say, okay, what are they? Classification. Stable, things move towards you. Unstable, things move away from you. Semi-stable, things move through you, is how you should think of it. And as time moves forward, you either move to one of these points, constant solutions, or you head off towards an infinity. How do you know which one you go to? Well, the answer is you just start. If I start here, where do I move? To the left until I hit that constant solution, and that's where I end up. So it's easy to see where you go to as time moves on to infinity. Our constant coefficient, ODEs, favorite kind, it says, hey, take your differential equation, turn it into an algebra problem. We find the roots. Each root comes up with a function. Put the functions together. That's superposition. And then we solve for the coefficients if we need to. Other things you should be able to do. This is our last piece. Know how to use the Wronskian. So the Wronskian is this determinant. Know how to set it up. How to carry out a determinant. You won't have to do anything bigger than a 3 by 3. So it's either a 2 by 2 or a 3 by 3. Know if it's equal to 0, it means it's linearly dependent. If it's not equal to 0, linearly independent. And then the spring mass systems we already talked about today. And that's it. That's what we learned. That's what you need to know for the exam.